Okay, hi everyone. Thanks for coming to my talk. It's a more beginner-focused talk, so I think after Marcus' talk, it's gonna feel like a rest for your brain. English is not my mother tongue, and it's my first talk in English, so please be forgiving. So today I'm gonna talk about functors, which are one of the main tools in our FP toolbox. My name is Martin Menestret. I work at Ibis Next, which is an awesome French consulting company with a strong focus on data science and data engineering. I'm a software engineer there. I work remotely from Nantes, which is a French city, and I'm doing my best to try to organize the Scala Nantes meetup, so feel free to come if you're nearby. And if you want to follow me, that's my Twitter handle, and that's my blog. So, okay, at first, we're going to try to have an intuition about what functors are, a feeling about what they are, and then we're going to try to observe what they look like in practice in Scala. And then we're going to try to see what they are in theory, in the category of theory of a category. And then we'll go back to concrete stuff and try to bridge the gap between theory and practice. Okay, so let's try to give you an intuition about what functors are. First of all, there is no perfect metaphor for functors, so I'm going to use an imperfect one, which might not fit every cases, but I think it's still good enough to get the feeling about what they are. So we're going to consider functors as containers, but really generic containers. Containers, we do not care about details, we do not care about particularities, and for example, we do not care about how to access data they may contain. So there is something more important. It's that these containers' content can be changed. It can be mapped or transformed by transformations. And the container itself is going to remain the same, but the content is going to be changed. So the containers stay the same, but the content inside can be changed. And it has to obey two main rules, which is identity and composition, and I'm going to talk about that later. So let's try to observe what they look like in practice. We're going to play around with a few different containers, a few different functors. So this is the function we're going to use to transform their contents. And it's an awfully complex function that's going to take an int and return a Boolean. It's going to return true if the int is 42 and false otherwise. So let's observe how options work. So here we have an option of int, an option containing an int, which is 42. And then we're going to use map. Map is a function. You give it a transformation and a container, a functor, and then it's going to apply the transformation to the content of the container. So here we can observe that we have an option of int, and when we map his magic on it, then we get back an option of Boolean. Same goes here with list. We have a list of int, and then when we map his magic on the list, then you get back a list of Boolean. Here, we created our custom container, which is called container, and it's going to contain a value of type A. So we create a container of int containing an int, and then when we map our transformation on it, once again, it gives back a container of Boolean. So the map function captured this pattern, which is map is a function that takes an f of a, which is our container containing values of type A, and a function from a to b and gives back an f of b. So the main parts are there. It's a f of a, it takes an f of a function from a to b, and gives back an f of b. So to illustrate how map works, here is a nice illustration that you can find on the internet. Map takes a container, which is a gift right here, and unwrap its content, if it have any content, apply the transformation on it, and then stuff it back in the same container, leaving the container unchanged, but the content has changed. So to sum up, the functor f is a container whose content can be changed, and it has to follow some rules. But how is it implemented in Scala? Okay, so in Scala, a functor is encoded as a type class. So a type class, just a quick reminder, is a set of type, a class of types, hence the name type class. So a family of type satisfying a common interface and laws. So here I try to give you a small illustration. On the left, you have a lot of different shapes. Well, a lot of triangle, but different color, different size. And what we can see is that the common pattern, the common contract is they are all being triangle. So being a triangle would be the type class. And on the left, the different triangle are our types, are specific instances, and they all are member of the type class being a triangle. So being a triangle is the type class, and maybe for the type class we can have a law which would be the sum of the three angles should be 180 degrees. So being a triangle is the type class, and on the left is our different specific types, member of the type class. On the right, the same example, we have different shapes, different size, but all of them are orange. So being orange would be the type class, and all of the different example would be the specific instances of our type class. So a type class in Scala is encoded by, it's not a first class citizen, so it's encoded by a trait, taking a type parameter, and for each concrete types wanting to be a member of that type class, a member of that family, you have to supply an implicit instance for that trait, for that specific type, and you should also prove that each type class instances that you create are respecting the type class law if the type class has some law. So here is a simple example. Show is a pretty simple type class. It's the family of all the types whose values can be turned into string. So any type that can be turned into strings can be a member of the type class show. And we can see it's a trait taking a type parameter and exposing a contract, the print function, which take a value of the type A and turning it into a string. So in order to be a member of the show type class, you have to provide for the specific type, the specific implementation of show for that type. And here is how you create an instance of show for int. You create a new show, a new instance of show with the specific implementation of your print function for int. Okay, so now let's look what our functor type class looks like. Our functor type class is there, and the first thing to notice is that the type class expects not a concrete type, but a type constructor. So just a quick recap about type constructors. A type constructor is a feature allowing you to create new types. So as an example, list is not a concrete type. You cannot create something of type list. List has to get a type parameter to provide a concrete type. And for example, if you give list int, then you get a list of int, and you can create new values of type list of int. But list itself is not a concrete type. It's a type constructor. So same goes here for map. Map takes two type parameter, one for the type of the value, one for the type of the keys. And then you get back a concrete type, and you can create values of it. Container, our container that we just created earlier, is also a type constructor. You can give it a Boolean, and then you get back a container of Boolean. So that's the type constructors. So back to our functors. The type class, the functor type class, expect as a type parameter a type constructor, and it exposes the type constructor makes sense here because it represents the possibility for a type to hold another value, to hold the value of another type. So it makes sense. And our type class exposed the map function that we just saw earlier, that we observed. And the map function takes an f of a, which is our generic container, a value from a to b, and gives back an f of b, which is a container holding values of type b. And here is the implicit instance you have to provide for our container for it to be a member of the functor type class. So this is a new instance of our trait. Container is a type constructor, so you can provide it to the trait. And this is the concrete implementation of map. for our container, which is pretty simple. It takes the value inside the container, it applies the function on it, and then it stuffs it back into a container. Okay, and then we should probably check if our new instance of functor of container respect the functor laws, being identity. Identity means that if you map a function onto your container, then you should get back the same container unchanged with the content unchanged. And the associative composition, which is if a container is mapped over once by a function, and then the result is mapped again by another function, it should give the same result as if you had mapped only once with the composition of your two transformations. Laws checking can be done with a nice library called Discipline, but you can safely use cats or Scala-Z functors, the functors that the that the libraries provide, because their laws are already checked for you in the library tests. Okay, so now let's try to look like what to observe what they look like in theory in the category of a theory of category. Okay, so simply put, a functor is just a structure-preserving mapping between two categories. Well, that might be not that clear, so let's try to dissect that definition step by step. First of all, what is a category? Well, a category is the subject of study of theory of category. And what is category theory? Well, my informal definition would be the study of a relation between things. But no matter what are the things, any kinds of things, it might be relationship between family members, it might be order between things in a set. So we don't care about the things, we care about the relation between things. So it's the study of the relations between things. It might be simple like that, but it can break a mind faster than you think. So in category, theory of category, a category is always composed by a few elements. There are objects. The objects are the thing in my definition, the study of relation between things. So objects are the things. The arrows or morphisms are the relations between things. And to complicate things just a bit, there is two rules that a category has to obey. The identity rule, which means that every object of your category has to have a morphism, so a relation between it and itself. And the associative composition, which means that for if there is a morphism from an object to another, from an object A to an object B, and then a morphism from an object B to an object C, then it must exist a morphism between A and C, which is the composition of the first two. And for the associative part, if you have three morphisms, F, G, and H, then the composition of F and the composition of G and H should be the same as the composition of F and G and then composition of H. The order doesn't matter. It's just like when you add integer. So that's the associative part. Here's a simple category. You have three objects, A, B, and C, and then you have morphism, which are F, which is the morphism from A to B, G, which is the morphism from B to C, and G compose F, which is the morphism from A to C. So the laws here are, we have to have G compose F, because we have a morphism from A to B and morphism from B to C, then G compose F has to exist for it to be a real category, a correct category. And we have three other morphisms, which are 1A, 1B, 1C, which are the identity morphism from each object to themselves. All right, so done with the abstract definition for now. Now let's try to see how it relates to Scala. So in Scala, there is a very special category to consider, which is called scal. And scal is going to be of prime interest for us. So the objects of scal are going to be Scala types. And the morphism of scal are going to be a function between those types. And it respects the category rules identity, because in Scala we have the identity function which maps any type to itself, and the associative composition, because in Scala function compose first, and then the composition is associative. So we have all ingredients to consider Scala as a category, but I have to give you a precision. Scala is not rigorously a category. This is a theoretical concession that we make, because, for example, in a real category, for example, family membership, or relation between family members, the morphism, so the relation between people of a family, exist. They just exist. In Scala, our morphism are functions. Functions are computations, and computations does not just exist. They are functions, and we have no way to know if a function is going to terminate, if it's going to fail, and so on. So it's a theoretical concession to consider Scala as a category. This is one of the examples why Scala is not rigorously a category, but we're just going to consider it is. So about our objects and morphism, just to sum up. For example, int or list of Boolean or unit or any Scala types are going to be our object in Scala category. And functions from type to type, so for example, into string and so on, are our morphisms. And our laws, so given three functions, f, g, and h, then we know that f and then g and then h is going to give the same function as f and then g and then h. So it's okay for associative composition. And in Scala, the parametric identity function is going to map any type A to the type A. So for any type, we're going to have the identity morphism. So the laws are okay. So that might make sense to study what category theory might give us, because Scala is a category and we work a lot in Scala. Okay, so go back to our difficult functor definition. So a functor is a structure preserving mapping between two categories. So what does it mean? It means that if we get two categories, S and S prime, then a functor between S and S prime is going to map objects from S to objects of S prime. And it's going to map morphism from S to morphism of S prime, while preserving the morphisms and preserving the composition between morphism, which means that if in the first category we have two objects that are connected, then their images are going to be connected in the second category. And the composition between morphism are going to be respected. So we are going to focus on endofunctors, which are a special kind of functors, which are mapping a category into itself. So a functor maps two categories. Well, the second categories can be the same as the first one. So endofunctors are mapping a category into itself. So in our case, in Scala, endofunctors are going to map Scala types to Scala types. And they're going to map Scala functions to Scala functions, because our object in Scala are Scala types, and our morphisms are Scala functions. So with endofunctors, it maps Scala types to Scala types and Scala functions to Scala functions. So let's study an example to clarify all that. We'll see how options behave, and in particular the option type constructor, how it affects Scala objects. So for a generic type A, if you apply A to option, to the option type constructor, then you get back an option of A. If you give option int, you get an option of int. If you give to option type constructor a string, you get back an option of string. So I think it's pretty clear here how the option type constructor maps objects to other objects, Scala types to other Scala types. Okay, so that was about the objects. And what about the morphisms? So let me remind you the map function that we saw earlier. It was taking a functor f of a and a function from a to b and giving back an f of b. So if we keep that function in mind and we partially apply that function with a function from a to b, Then you give back, you get back a new function, which is needing only one parameter and of the type f of a, and which gives back an f of b. So we can imagine, and I'm going to show you some examples, that map promotes function from a to b to function from f of a to f of b. Okay, so for the identity function, we get a function from a to a, and when you partially apply map with that function, then you get back a function from option A to option A. Same goes for a to b, it gets mapped to option A to option B, and same goes for a simple function from int to string, it gets back from, it gets maps to a function from option int to option string. So I think it's pretty clear here as well that map is gonna map functions from Scala types to Scala types, okay? So it's the mapping from Scala to Scala, which is done by the option Endofunctor. Okay, so let's try to go back to practice. What functors do bring us? First of all, functors are abstractions, and abstractions are pretty great because they allow you to focus on what really matters. They abstract over any kind of containers which may contain values and whose content can be mapped over. So they constrain your implementations, and that constraint gives you power. It liberates you, as Runar would say in this great talk. So these abstractions make your code less error prone, since the only thing you know and you can do with something with only knowing it's a functor is just calling map over it. So it really reduces the opportunity for errors, and it's allow you to forget about implementation detail, how to access the data, and so on. So you just have less opportunity to make errors on your implementations. And it's also enhanced the code reuse, because an implementation only based on the fact that something is an abstraction, in that case a functor, then you can call that implementation with any kind of functor, it's gonna just work. But it's not only about the abstraction, because functors, as they have also concrete instances, and these instances has a lot to offer. So for example, options can express the fact that a value might be missing, an absence of value. Either can, for example, but either can do a lot of things, but express computation errors. And IO can, for example, express a computation recipe or a computation process, and so on. So you will still be able to use your original types, original functions, and their compositions. But once the types are wrapped in those functors, then thanks to the structure preserving natures of the functors, the endofunctors that we just saw, you will still be able to use your function and so on, and you will get the benefits of the concrete data structure behind functors. So to sum up what we saw, functors are containers whose content can be mapped over. They are encoded as type class in Scala. Category theory tells us that they are mapping between categories. Now we know that Scala is a category of Scala types and function between them under function composition. And we saw that functors are mapping between Scala to Scala, so Scala types to Scala types, and Scala function to Scala functions. And we just saw the superpower it might give us. So there is a couple of links if you want to dig deeper. And thank you a lot for your attention. Sorry, I might have been a bit quick. Maybe the stress effect. Yes?
You mentioned the Scala thing being about functions in Scala, but I've only seen functions with one argument.
Yes.
So you handle more than one.
That's a really good question. I think That might be where applicative comes into play. Functors are just about single argument functions, well, in category terms. So yeah. Yes?
You would take any two argument functions and turn them and carry them, right? You would get
Yeah. Yeah, you could.
only one argument.
Yes, yes, yes.
I can have a question also. Like you showed how map lists functions. Can you elaborate on how you list objects?
How do we lift objects? Well, it's when you have like a functor type constructor, then when you apply a type, well, when you apply a type to that type constructor, it lifts it map your original type, for example, int with option. It lifts int to option of int, which is a new type. So you get your object from scal, which is int, to a new type, option of int, which is another type of scal. So that's how objects are mapped. It's like a function on objects. Functors are like function on objects and function on morphisms. So that's the object part. It's through the type constructors. Okay, thanks again.